Well, you've made it safely past logarithms. Welcome to lesson 3 in Math 222. This deals with exponential functions, and you will remember exponential functions from your high school algebra courses, but of course here in a calculus course we're going to deal with it with respect to derivatives and integrals and the like. So let's refresh our memory. The natural log function was that function that looked like so. It passed through 1, 0. It passed through E1. This is the natural log function. And then we're going to take an idea from our first lesson that if I want to find the inverse of this function, and I can certainly find the inverse of this function, and I know that the inverse of this function will be a function because this is an increasing concave down function. It's 1 to 1. And since it's 1 to 1, I can reflect over y equals x and get the inverse function, and that of course will be a function. So how do I get an inverse function? Well, 1, 0 becomes 0, 1. E1 becomes 1e, and you get some graph that swoops up like this. And as you well remember from high school, this is the graph of y equals e to the x. So because the exponential function and the logarithmic function are inverses of each other, there are some consequences. One that's really important to remember is that e to the ln of x is x for positive x's. And it has to be positive x's because we're taking a natural log of x. And we can only take a natural log of a positive argument. Again, they're inverse functions. So if we substitute one into the other, we end up with x. But of course, that goes both ways. If I take the one and sub it into the other, I get x back. And this is true for all x's because you can raise any number. You can use any number as an exponent for e. And this will always be positive, so you're always taking the natural log of a positive number. So these are a couple of nice things to have in your back pocket. Those are properties that we use somewhat frequently. Okay, this is the exponential function. It's got all the familiar properties that exponential functions have. If you multiply powers of the same base, you add their exponents. There are lots of good reasons why that's true. Similarly, dividing powers of the same base results in subtracting exponents. Sort of by definition, but not really. E to the minus p is the same as 1 over e to the p. This is one of those things that almost makes sense if you think about it. Try cross-multiplying to make sure that that does in fact make sense. Try cross-multiplying. And the other rule that we use with some frequency, power to a power. When you have a power to a power, those exponents multiply. Then there's the black sheep in the family. What if your base is not e? What if you have some other number to the x power? How can I connect that to e? Well, a to the x is the same as e. Wow, that was just ugly. E to the x times ln a. And the reason why that works, this is a quick explanation, but it does work. This is the same as this is the same as this. So we have e to the ln of a to the x. And we know from the previous slide, that e to the ln of a is a. And so this is equal to this, which is equal to that because of that. This guy we have to keep in our toolbox. We are going to need him. Some might ask, as a very interesting side note, as a side note, you may wonder, what is E in terms of something that a calculus student would appreciate? Well, E can be expressed as a limit in a couple of ways. It is the limit as x approaches infinity of 1 plus 1 over x to the x. Or if you don't like limits at infinity, it's the limit as x approaches 0 of 1 plus x to the 1 over x. And this is the one you probably saw in high school where a teacher said, let's invest $1 at some interest rate and let's compound it a zillion times and see what happens. That's this definition that generally is used in the Algebra 2. Okay? There's a proof of this that's not terribly difficult to understand. So we'll give it a go. If f of x is the natural log of x, then f prime of x is 1 over x. You remember that, don't you? So consider the following. Bill Nye the Science Guy. What is f prime of 1? Well, f prime of 1 is the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. So this is the limit as h approaches 0 of 1 over h times the natural log of 1 plus h. Now, you and I both know when you have a number in front of a natural log, that's this. And that's starting to look like something we know about. So here's the thing. F prime of 1 is 1, which means that this quantity approaches 1 as h approaches 0. And if the natural log of a quantity approaches 1, then that quantity itself approaches e. And once you establish this, it's really easy to establish that. And I'll let you figure that out in the privacy of your own home. We should do some calculus type things. For example, we know that this is true. We know the natural log of e to the x is x. That's from a couple of slides back. You can thumb back if you need to, which means that the derivative of the natural log of e to the x is 1. How am I doing so far? Well, of course, you remember how to take the derivative of a natural log. The derivative of a natural log of something is 1 over the something times whatever the derivative of that something happens to be. So if I wanted to know what the derivative of e to the x is, I could just cross multiply. The derivative of e to the x is e to the x. That's a big deal. That's a big deal. The exponential function is the non-trivial function whose derivative is itself. There are others, they're all multiples of this, but this is the standard non-trivial function whose derivative is itself. We love it for that reason. The downside for you is that we calculus teachers exploit that in a variety of ways. So we do things like ask you to differentiate. We ask you to differentiate. And that's not too terribly awful, I don't think. We could ask you to differentiate e to the cosine x. And you would say to yourself, self, I know how to do that. The derivative of e to the something is e to the something. Chain rule says I have to multiply by the derivative of this something, and I'm done. And you're right, you're done. That's it. Or I might ask you to do something a little bit weirder. I might ask for the derivative of e to the x times x to the e. And you would remind yourself of stuff you learned in Calc 1. The product rule is so much fun. It's 1 prime 2 plus 2 prime 1. So derivative of the first times the second. Well, the derivative of the first, that's the derivative of e to the x, that's e to the x, not bad. Plus the derivative of the second times the first. The derivative of the second, now that's an interesting thing. This is x to a numerical power. And how do we find the derivative of x to numerical power? That's ex to the e minus 1. And we would leave this exactly as is, because to do any different would just be crazy. You may want to make sure, because we'll talk about it when we gather, that you know how to take the derivative of that. That may be something you may want to remember how to do. And then we calculus teachers do crazy things like, say, integrate. And that's not too bad when you're dealing with something like this. Is it? If what I know is that the derivative of e to the x is e to the x, then I'm pretty sure that the integral of e to some variable power is going to involve e to that variable power, but I'd really like e to the u du. And the only way to get e to the u du is to let u be 2x. I don't want to be 2x. And then du is 2dx. So this turns out to be 1/2 the integral of e to the u du from 0 to 2 ln 4. Notice the change in the limit there. So what is that? Well, that's 1/2 e to the u from 0 to 2 ln 4. And that's 1/2 e to the 2 ln 4 minus 1/2 e to the 0. And I'll leave it up to you to convince yourself that that's 15/2. I'm going to leave that to you to figure. You have to be able to get from here to there. Because when you check yourself in the back of the book, you're going to see this answer, but you're going to do this and want to make sure that that's the same thing. It might be an interesting exercise for you to do the integral from 0 to 4 of e to the radical x over 2 radical x dx. That would be a very interesting exercise for you to do. One more thing before I turn this thing over, and that's what about other exponential functions? How do you take derivatives and integrals for other exponential functions? Well, if I'm looking for the derivative of some other number to the x, then I go back a couple of slides and I realize that that's the derivative of e to the x times ln a. And then I remember, how do I take the derivative of e to the something? Well, that's e to the something times the derivative of that something. This is a linear function. It's no different than taking the derivative of 10x or 100x or 1000x. This is a number times x. So the derivative of x ln a is just ln a. And then I find a nice way to rewrite that. E to the x ln a was a to the x in the first place times ln a. The derivative of some number to the x power is that number to the x power times ln of that number. And for similar reasons, the integral of a to the x dx is a to the x over ln of a plus a constant don't forget your plus a constant. So just to demonstrate, if y is 5 to the sine x squared, and I'm interested in dy dx. Well, the derivative of 5 to the something is 5 to the something times the ln of 5 times the derivative of the something. And the derivative of sine something is cosine something times the derivative of something, and I'm done. The other thing that we should talk about is what happens with integrals like 3 to the x squared plus 2x times x plus 1 dx. And you're thinking to yourself, that looks like a u because that looks like the derivative almost of that. So u is pretty easy to figure, and so is du. So we throw the 2 in there and the 1/2 like so, and we get 1/2 times the integral of 3 to the u du, and I know how this goes. The antiderivative of 3 to the u is 3 to the u over ln 3. Don't forget your plus a constant. Those are things you should know how to do before we gather in class again. All right, so you've stuck with me for about 17 minutes, and that's probably all you can do, and that's that. So I will see you when we gather, and look forward to the meeting.